The universe is growing. Right now, as you listen to these words, space itself is stretching. Every galaxy, every star, every atom of existence is drifting further apart. But here's the question that haunts physicists in the dead of night. Growing into what? We can measure the acceleration. We can trace the redshift of distant galaxies. We can map the cosmic microwave background with exquisite precision. But we cannot answer the most fundamental question of all. Where is it all going? What lies beyond the edge of everything? The universe is expanding into nothing, an absence so profound that it defies every human intuition. A void that is not simply empty space, but the negation of space itself. A silence beyond silence. A darkness deeper than any darkness we can imagine. The more we look outward with our most powerful telescopes, the more we realize that the cosmos is racing towards something unfathomable. Or perhaps it's racing away from something. Or maybe there is no difference between the two. The universe stretches, accelerates, and dissolves into an abyss that should not exist. What does it mean for something to expand into nothing? How can infinity itself grow larger? These questions don't just challenge physics, they challenge the very foundations of logic, of reason, of what it means for anything to be real. Even Einstein's equations trembled before this truth. What once seemed like a simple question of geometry became an existential riddle wrapped in mathematics. The universe is not just big, it's not just old, it's actively racing toward its own dissolution, and the mechanism driving this flight is more mysterious than anything we've ever encountered. As the universe grows older, the stars will fade one by one. Galaxies will vanish beyond an unreachable horizon. The last remnants of matter will drift through an eternal darkness, separated by such vast distances that they might as well be alone in their own private universes. The cosmos is becoming lonelier with every passing second. Physicists do not fear the void because it is vast. They fear it because, according to everything we know about reality, it should not exist. Empty space should not have energy. Nothingness should not push. The vacuum should not scream. Yet it does. This is the story of a universe expanding into absence, a cosmos unraveling toward the unthinkable, and the minds who dared to ask a question that may have no answer. Can something infinite still be lonely? The first glimpse of infinity. In 1929, at the Mount Wilson Observatory in California, an astronomer named Edwin Hubble made a discovery that would shatter humanity's understanding of existence itself. He wasn't looking for the end of the universe. He was simply measuring the light from distant galaxies, trying to understand their motion through space. What he found was impossible. The galaxies weren't standing still. They weren't orbiting some cosmic center. They were fleeing, every single one of them rushing away from us at tremendous speeds. And the strangest part? The farther away a galaxy was, the faster it was moving away from us. Imagine standing in the center of a vast room where every person around you suddenly starts running. The people closest to you jog. The people at the edge of the room sprint. The people you can barely see in the distance move faster than you can comprehend. That's what Hubble saw in the cosmos. A universal flight, an exodus of galaxies. But flight implies something to flee from. Flight requires space to move through. And that's where the true mystery began, because the galaxies weren't moving through space. Space itself was expanding, carrying the galaxies with it like raisins in rising bread dough. This was not a simple discovery. This was a revelation that rewrote reality. For thousands of years, humanity had assumed the universe was eternal and unchanging. The stars wheeled overhead in their ancient patterns. The cosmos was a stage, and we were merely players upon it. But Hubble's observations suggested something far more unsettling. The stage itself was growing. The theater of existence was expanding into what exactly? Before Hubble's discovery, there were hints, whispers in the mathematics. A few decades earlier, Einstein had developed his theory of general relativity, a revolutionary framework that described gravity not as a force, but as the curvature of space-time itself. Mass and energy warped the fabric of the universe, and objects moved along the contours of that warping. When Einstein applied his equations to the universe as a whole, he encountered a problem. The mathematics suggested that the universe could not be static. It had to be either expanding or contracting. This horrified Einstein. The universe was supposed to be eternal, unchanging, perfect. So he did something remarkable. He modified his own equations. He introduced a term called the cosmological constant, a kind of repulsive force that would perfectly counterbalance gravity, holding the universe in a delicate, eternal balance. It was an elegant mathematical trick, a way to force the universe to behave the way Einstein believed it should. But the universe does not care what we believe. Around the same time, a Belgian priest and physicist named Georges Lemaitre was exploring Einstein's original equations without the cosmological constant. Lemaitre's mathematics suggested something radical. If the universe was expanding now, then if you ran time backward, it must have been smaller in the past, much smaller, infinitely smaller. Lemaitre proposed what he called the primeval atom, the idea that the entire universe, with all its matter and energy, once existed in a singular, incomprehensibly dense state, a cosmic egg that hatched in a moment of creation. The birth of space and time itself, Einstein dismissed the idea. It was too strange, too theological, too much like creation mythology dressed in mathematical clothing. But Lemaitre persisted. His calculations were sound. The universe had a beginning, and it was expanding. Then came Hubble's discovery, the mathematical prophecy confirmed by telescopic reality. When Einstein learned of Hubble's discovery, he traveled to Mount Wilson to see the evidence for himself. After examining the data, he reportedly said that introducing the cosmological constant was the biggest blunder of his life. The universe was dynamic, growing, evolving. It had been trying to tell him this all along, but he had refused to listen. But Hubble's discovery opened more questions than it answered. If the universe is expanding, what is it expanding into? If space itself is growing, what exists beyond space? These questions haunted physicists for decades. They still haunt us today. In the decades following Hubble's discovery, astronomers continued measuring the expansion. They developed better techniques, more precise instruments. They calculated what's now called the Hubble constant, a number that describes how fast the universe is expanding at any given distance. But measuring this number proved to be one of the most difficult challenges in all of science. The farther you look into space, the further back in time you see. Light takes time to travel. When we look at a galaxy a billion light years away, we're seeing it as it was a billion years ago. The universe has expanded during the time it took that light to reach us. This creates a kind of cosmic illusion, a hall of mirrors where distances and times become entangled. By the 1960s, physicists had developed a reasonably good understanding of cosmic expansion, or so they thought. The prevailing assumption was simple. The universe expanded rapidly after its birth in the Big Bang, but that expansion should be slowing down over time. Gravity, after all, is attractive. It pulls things together. The collective gravitational pull of all the matter in the universe should be acting as a cosmic brake, gradually slowing the expansion. Some physicists even debated whether there was enough matter in the universe to eventually halt the expansion entirely, causing the cosmos to collapse back in on itself in a big crunch. Others argued there was just enough expansion velocity to overcome gravity, allowing the universe to expand forever but at an ever-decreasing rate. Either way, everyone agreed on one thing: the expansion must be decelerating. Then in 1965, two radio astronomers at Bell Labs made an accidental accidental discovery that would confirm expansion's reality in the most unexpected way. Arno Penzias and Robert Wilson were trying to eliminate persistent background noise in their radio antenna. No matter what they did, they couldn't get rid of a faint hiss that seemed to come from every direction in the sky. They checked for interference from nearby New York City. They cleaned out pigeon droppings from the antenna. They recalibrated their instruments again and again. The noise remained. Uniform, persistent, mysterious. What they had discovered was the cosmic microwave background radiation, the afterglow of the Big Bang itself. When the universe was very young, just a few 100,000 years old, it was filled with a hot, dense plasma of particles and radiation. As it expanded and cooled, that plasma became transparent, and light could finally travel freely through space. That ancient light has been traveling through the expanding universe ever since, stretching and cooling as space itself stretched, until it now appears as faint microwave radiation. This was the echo of creation, the whisper of the beginning, and it confirmed beyond any doubt that the universe had been incomprehensibly hot and dense in its infancy and has been expanding and cooling ever since. The cosmic microwave background is remarkably uniform across the sky, with only tiny variations in temperature from one region to another. This uniformity told physicists something profound. The universe must have expanded from a highly ordered initial state. The early universe was smoother, more homogeneous than anyone had anticipated. But that uniformity itself became a puzzle. Different regions of the universe, now separated by vast distances, all have the same temperature to within 1 part in 100,000. How did distant parts of the universe, which could never have been in contact with each other, even traveling at the speed of light, come to be so perfectly uniform? This became known as the horizon problem, and it led to another revolutionary idea: cosmic inflation. In the first tiny fraction of a second after the Big Bang, the universe expanded exponentially, growing by a factor of perhaps 10 to the power of 30 or more. This rapid inflation smoothed out any initial irregularities and set the stage for the more sedate expansion we observe today. Inflation solved several puzzles, but it also raised new questions. What caused inflation? What kind of energy field could drive such rapid expansion? And most unsettling of all, if inflation could happen once, could it happen again? By the late 20th century, physicists had assembled a coherent picture of cosmic history. The universe began in a hot, dense state. It underwent a brief period of exponential inflation, then it settled into a more gradual expansion, cooling as it grew. Galaxies formed from tiny density fluctuations. Stars ignited, planets coalesced, and through it all, the expansion continued, gradually slowing down as gravity exerted its influence. This was the standard model of cosmology: elegant, consistent with observations, and broadly accepted. There was just one problem: it was completely wrong. Chapter 2: The Acceleration. The 1990s were supposed to bring closure to cosmology. After decades of increasingly precise measurements, physicists were ready to pin down the exact rate at which the universe's expansion was slowing down. Two independent teams of astronomers set out to measure this deceleration using a specific type of exploding star called a Type Ia supernova. These supernovae are remarkable objects. They occur when a white dwarf star accumulates enough matter from a companion to reach a critical mass, triggering a thermonuclear explosion. Because they always detonate at roughly the same mass, they always reach roughly the same peak brightness. This makes them perfect cosmic measuring sticks. By measuring how bright they appear from Earth compared to their known actual brightness, astronomers can calculate their distance with remarkable precision. The plan was simple: measure the distances to many supernovae at different points in cosmic history. Compare those distances to their redshifts, which tell us how much the universe has expanded since their light was emitted. Plot the relationship between distance and redshift. The shape of that relationship would reveal the deceleration rate. Both teams worked independently, competing but also checking each other's work. They scoured the sky for supernova. They measured their brightness meticulously. They calculated distances and redshifts. And as the data accumulated, something strange began to emerge. The distant supernova weren't where they were supposed to be. They were dimmer than expected, which meant they were farther away than they should be. But this made no sense. If the expansion was slowing down, those distant supernovae should have been closer, brighter. Instead, they were receding faster than anticipated. At first, the astronomers assumed there was an error. Perhaps interstellar dust was dimming the light. Perhaps the distant supernovae were intrinsically different from nearby ones. They checked and rechecked their data. They looked for systematic errors. They found none. The conclusion was inescapable, and it was shocking. The universe's expansion was not slowing down. It was speeding up. In 1998, both teams announced their results almost simultaneously. The acceleration of cosmic expansion, a discovery so unexpected that it would be awarded the Nobel Prize in Physics just 13 years later. But the Nobel Prize came with a terrible gift, a mystery so deep that it threatened to unravel our entire understanding of physics. If the expansion is accelerating, something must be driving that acceleration, some form of energy that acts opposite to gravity, pushing space apart rather than pulling matter together. The physicists gave this hypothetical energy a name, dark energy. The name is misleading. It's not dark like dark matter is dark. It's not matter at all. It's not even really energy in any conventional sense. It's a placeholder for our ignorance, a name for something we cannot see, cannot detect directly, cannot understand. And yet it dominates everything. Further observations confirmed and refined the initial discovery. Physicists calculated that approximately 68% of all the energy in the universe exists as dark energy. Not 68% of the matter, 68% of everything. The stars, the galaxies, the planets, even the dark matter that outweighs ordinary matter 5 to 1, all of it together makes up less than a third of the universe's total energy budget. The rest is dark energy, the force driving the acceleration, the entity pushing the universe into the void. This discovery shattered cosmological assumptions. Every model, every prediction, every understanding of the universe's fate had assumed that gravity was the dominant force on cosmic scales, attractive, inevitable, eternal. But dark energy revealed that there was something else at play, something repulsive, something that wanted space to expand. The immediate question was, what is dark energy? Einstein's cosmological constant, the term he had introduced and then discarded, suddenly became relevant again. In his original formulation, the cosmological constant was a property of space itself. Empty space, according to this idea, has an intrinsic energy, and because space is constantly expanding, creating more of itself, that energy grows with it. The more space you have, the more dark energy you have, and the faster the expansion accelerates. This was elegant in its simplicity. Space itself was the source of the acceleration. No exotic fields or particles needed, just a fundamental property of the vacuum. But there was a problem, a catastrophic problem. When quantum physicists calculated what the energy of empty space should be based on quantum field theory, they got an answer that was roughly 10 to the power of 120 times larger than what cosmologists observed. This became known as the worst prediction in the history of physics, or the cosmological constant problem. Imagine trying to calculate the weight of an apple and getting an answer equal to the mass of the entire observable universe. That's the level of discrepancy we're talking about. Something was profoundly wrong with either our understanding of quantum mechanics, our understanding of gravity, or both. The alternative explanation was that dark energy was not a constant property of space, but rather some kind of dynamic field that changed over time. Physicists called this hypothetical field quintessence, after the classical fifth element. Unlike the cosmological constant, quintessence could vary in strength and density as the universe evolved. This idea had some appeal. It could potentially explain why dark energy seems to have the right amount at the right time to become dominant, just as intelligent life evolved to observe it. But it also raised new questions. What kind of field is quintessence? Why does it have the properties it does? How does it interact with matter and radiation? Every answer generated new mysteries. As physicists grappled with these questions, they began to realize the implications laws of accelerating expansion. If dark energy remains constant or grows stronger over time, the universe's fate is sealed, not in fire, but in ice, or more accurately, in absolute emptiness. Galaxies are already moving away from us. The farther away they are, the faster they're receding. And here's the key point. Because of the acceleration, galaxies beyond a certain distance are receding faster than the speed of light, not moving through space faster than light, which would violate relativity, but being carried away by the expansion of space itself, which has no speed limit. This creates what's called the cosmic event horizon. Beyond this horizon, light emitted today will never reach us. No matter how long we wait, the expansion is carrying those regions away too quickly. They are leaving our observable universe forever. And this horizon is shrinking. Right now, we can see galaxies billions of light years away. But in the far future, most of those galaxies will have crossed the cosmic horizon. Their light will be stretched to infinite wavelengths. They will fade from view and never return. The universe will become a lonelier place. Eventually, only our local group of galaxies, bound together by their mutual gravity, will remain visible. The rest of the cosmos will have vanished beyond the horizon, leaving us in an island universe surrounded by an infinite, empty void. But even that's not the end. As expansion continues, that local island will slowly erode. Stars will die, black holes will form, and after an unimaginable span of time, even the black holes will evaporate through Hawking radiation, leaving nothing but scattered particles separated by vast gulfs of space. This is the heat death of the universe, the final equilibrium, a state of maximum entropy where nothing can ever happen again because there's no energy gradient left to drive any process. The universe doesn't end in a moment. The acceleration is real, the mystery is profound, and the search for answers is just beginning. It fades, gradually, over timescales that make the current age of the cosmos seem like an eye blink. But buried within this grim prognosis is an even more disturbing possibility. What if dark energy is not constant? What if it's growing stronger over time? Then the acceleration could become so extreme that it tears apart not just galaxies, but solar systems, planets, atoms themselves. The more we learned about the acceleration, the more the mystery deepened. Dark energy doesn't just dominate the universe's present and future, it raises questions about the past, about the nature of space and time, about the very laws of physics. Why is dark energy's density so small compared to quantum predictions, yet large enough to dominate the cosmos now? Why did matter and dark matter dominate the early universe, with dark energy only becoming important relatively recently? Is this timing a coincidence, or is there some deeper connection? And beneath all these questions lies the most fundamental mystery of all. What is the quantum nature of the vacuum itself? What is this empty space that drives the expansion? What secrets does it hold? In the next part of our journey, we'll dive deeper into the quantum paradox at the heart of dark energy. We'll explore how physicists are mapping the expanding void, measuring the acceleration with unprecedented precision, and confronting the possibility that the vacuum itself might be unstable. We've discovered that the universe is accelerating. Now we must understand what that really means for physics, for reality, for existence itself. To be continued in Part 2, The Quantum Void, where we explore the deeper investigation of dark energy, the quantum nature of empty space, and the terrifying possibility of vacuum decay.